So now I'm going to discuss, I'm going to show you how to solve a statically indeterminate beam using moment distribution method. Okay, so now we have a beam here which is fixed support at A and internal roller at B, internal roller at C, and a 30 kilonewton load is acting at the free end D. So the question is, determine the end moments for the 3-span beam. So there are 3 spans. One is a cantilever span, then you have 2 internal spans. So I think we have approached this problem using slope deflection method. Now we will try to solve this using moment distribution method. So from the theory, what we have learned earlier, so basically we need to derive 2 things. First is the stiffness, that is a K. Okay, so the stiffness K of each beam. Then we need to derive distribution factor. Okay, so we have discussed this in earlier. So now we have, if you look at this point, this problem at support A, you have a fixed support and a member. So now this member, and there is a support, and it goes on like that, and this member AB is connected to a fixed support, and this is an internal pin, this is a fixed joint. So from our equations, where if the far end moment is fixed, your stiffness is 4EI over L. Okay, so we derive this one. So when the far end is fixed, the stiffness of the member, it is 4EI, so the bending stiffness is 4EI over L, that is the bending stiffness K. So if you consider this support, KAB is 4EI over L is 6, and EI is given as constant. There is no value for EI, so which means we'll keep it as EI. So now, if you have a moment at this support A, how that moment is going to be distributed? Or if we apply a load on this AB span, then that AB is going to deform, and when it's going to deform, it's going to induce some moment to keep it horizontal, keep the slope 0. So in that case, how this moment can be distributed? So if you look at the KAB is 4EI over 6, and K fixed support. So this fixed support, the stiffness of the fixed support is infinity. So if you look at the distribution factor AB, what would be the distribution factor AB, or what percentage of the moment is controlled by AB? Then it is KAB over KAB plus K fixed support. So Fs stands for fixed support. Okay, Fs fixed support. So now this is 4EI over 6, 4EI 6 plus infinity becomes 0. So this tells us that when a member connected to a fixed support, the member will not carry any moment. The entire moment or entire resisting moment carried by the support, because it has enormous bending stiffness. Now, if in a similar fashion, if you take BC, but the BC is, there are two ways you can approach BC. Okay, there are two ways you can approach BC. Now, if I recall the learning we had, so let me draw the BC. So here the B, here C. Now the component CD, okay, so B, C and D. The component CD, far end is free. Far end is free means this has no stiffness. This has no stiffness to the against the bending, because it can freely rotate that component CD. So one way to approach this is by converting that 30 into 4 as a moment and transfer at C. So if I do that, okay, so if I transfer that, so CD is a moment that is acting, so it's a moment acting like this, 120 kilonewton meter. So it can be replaced by a moment acting like that. Okay, so now if a moment acting like that, then now the C becomes a far end pin because we have removed the CD component and replaced with the moment. So C is a pin. So if I consider this scenario, here the B is an internal pin, so which is considered equivalent to fixed, and C is far end is pin. When the far end is pin, KBC is 3EI over L is 9. That is the stiffness of BC. Now, if you consider the distribution factor, so if you consider AB and BC, so at point B, so if there is a moment at point B, if there is a moment, if there is an internal moment at point B or at the support B, there are two members carrying that moment, BC and BA. So for any moment at B, distribution factor BA is KBA over KBA plus KBC. So this is 4EI over 6, this is 4EI over 6 plus 3EI over 9. So now EI cancels off. So if you take 18 as a common base, so 18 over 12 over 18, then here 18, 8 plus, no, it's 12. It's 12 plus, so 12, so 6 into 3, 18, 3 into 4, 12, 9 into 2, 18, 6. Okay, so that is 12 over 18 into 18 over 18. So that is 2 over 3. So if DFBA is 2 over 3, then DFBC is 1 minus 2 over 3, because the total is carried by the two components. So if the 2/3 is taken by BA, the 1/3 is taken by BC. So DF BC is 1 minus, that is 1/3. These are distribution factors. Now if I consider support C for any moment at C, now if you apply a moment C, so here in this case I am applying 120 due to the external. Now KF, so KBC is 3EI over L, L is 9, KCD, that is this free hanging component which has no bending stiffness, 0. So if I consider DFBC, that is KBC or DFCB, because it's CB, KCB over KCB plus KCD. So that is, KCD is 0, so it's 1. So in that case DFCD is 0. So DFCD is 0 because it's a free hanging element. So now we got the distribution factor and the bending stiffness. So now we have to carry out this moment distribution iterative procedure to obtain the results. Now doing this moment distribution is very simple. So now let me show you. This is, you draw a table. So here my app doesn't allow me to draw a straight line, so that is okay. So A, B, C, these are the 3 points. So A where there can be moment, B can be, and C, and D is a free end, so I'm not worried about D. Let me mark D also. Now if I divide this further into elements, okay, so AB at A, so here BA, BC, here CB, CD. Okay, so these are the segments. AB, when you consider support date AB, only one member. If you consider B, BA plus BC, so 2 member. Consider C, CB plus CD, 2 member. So now the next, what we should write down is, we should write down the distribution factor. Okay, so we have to have 2 things. One is distribution factor, other one is, so distribution factor for these. So if you consider AB, the distribution DFAB, we found it to be 0. So it is 0. Okay. So DFAB is 0. BA is here 2/3 and BC is 1/3. BA 2/3, BC 1/3, and CB is 1, CD is 0. Okay, so those are the distribution factors. Now we need to obtain the fixed end moments. This is similar to what we did for the slope deflection method. So if you consider the fixed end moments, if you consider FEM, here you have FEM, let me copy this. Okay, so so I'm going to delete this later, but just for the reference. So FEM AB, FEM BA, FEM BC, FEM CB, FEM CD. Okay. Now AB and BA. So if you consider the fixed end moment at A and B, so this is AB, this is BA. Okay, so FEM AB and FEM BA. So FEM AB, FEM BA. That is, if you have both ends, if A and B are fixed, you would have had a fixed end moment. But if you had A and B fixed, you had only 0 fixed end moment in this situation, because there is no external load acting on AB. Suppose if B and C are fixed, then you have FEM BC and FEM CB. Okay, FEM BC and FEM CB. So in this case, if you consider C, actually C we assumed as pin. We assumed C to be pin because we transfer the load to C, and then we assume C to be pin. So the far end is pin and B is fixed. So in such a case, I think if you look at the Hibbeler's book, so let me open that. So in the Hibbeler's book there are fixed end moments given, and if you look at the situation we have now, it is similar to this. So A is like an internal pin which is assumed to be fixed, and then the far end is pin. So in this case there is no moment acting at B due to the external load, but there is a fixed end moment at A, that is WL squared by 8. So if you consider here this component FEM CB is 0 because it is assumed to be a pin. That's why we got a stiffness, bending stiffness 3EI over L. So that is very important that we make this assumption, because we earlier assumed C to be pin. In that case we assumed 3EI over L. Now this is FEM BC. So FEM BC is WL squared over 8. So that is counterclockwise. So counterclockwise is positive. So WL squared over 8. So WL squared over 8. So that is so if I do the calculation, so here W is 10, L squared 9 squared over 8. Okay, so that is the fixed end moment, W squared over 8. So this one is 810 over 8, that is 101.25 kilonewton meter. So FEM BC is 101.25 meter, that is FEM CB is 0, but FEM CD is a counterclockwise. The reason is you are applying a moment, if you are applying a 30 load, so there is an internal moment, internal resistance, that is 30 into 4 counterclockwise, so that is 120. Okay, so now these are the fixed end moment. At AB you don't have a fixed end moment, BC you don't have a fixed end moment. Here it's 101.25, CB 0, CD 120. Okay, so 120 is so actually ABBC CBCD 120. Okay, so these are the values for the moments. Okay, so one thing I want to correct here is the sign convention. Similar to the slope deflection, in slope deflection also we consider clockwise moment that act on the member to be positive and counterclockwise are negative. So clockwise is positive, counterclockwise are negative. So the same sign convention here. So if you consider AB and BA are 0, 0, so we don't have anything, and BC is minus, and CB is 0, and CD is counterclockwise minus. Okay, clockwise is positive. So now what happens here is you have fixed end moments. At A there are no moment, at B, A and BC, if you consider B and BC, BA and BC, so that is, these are fixed end moments. But actually this is not a fixed support condition because it's a roller. So what happens is, if you have a 0 moment on this side and 0 moment minus 101.25 on this side, there's an unbalance. So you can imagine that we fix this and we release it. So it's now a pin, so it has to adjust and balance. So now due to external load, this is the moment acting on this. So now, so minus 101.25 here, CD is due to this external load, it is CD is acting clockwise, so that is plus 120. So it is acting as a moment on point C. So these are moments due to external loads. Okay, moments because the load is acting, there is a, this is, it tend to move it tend to deform, and this is a resistance if fixed in moments. So here also the 30 is tend to move this down, so there is a resistance that is counterclockwise minus 120. So now these are the, and now if you release this at B, there is an imbalance. So imbalance is here 0 at BA, at BC it's minus 101.25. So this, there is the imbalance. So that imbalance is now going to be balanced. So now there should be an internal balancing of 101.25, because the net moment at B should be 0. So if you sum MBA plus MBC, then I mean here the whatever we mark here is as MAB and MB and MBC. So MBA plus MBA plus MBC should be 0. Now here 0 plus minus 1.25, 101.25 is minus 101.25. So there should be a plus 101.25, and that plus, that's the internal mechanism. So that plus 2/3 of that comes from this BA element and 1/3 comes from BC element. So if you take plus 101.25, 2/3 of 101.25 is how much? So if you use a calculator, 101.25 into 2/3, that is 67.5. so 67.5 plus on from this member, and 101.25 minus 67.5, 33.75. okay, so we take 101.25 and 2/3 of that, 67.5. and so now if you sum the 0 and 67.5, it is 67.5. Here it is minus 67.5. So plus 67.5 and minus 67.5 are balancing, so that matching this compatibility of support B. If you consider the support C, again CB has 0 moment and CD has minus 120. So now there should be a plus 120, and that plus is carried by CB only. That is plus 120, because the distribution is C1 here, 0 here. Now this ends that full first balancing of all the moments. So now we know that there is the moment transfer or carryover moment that happens if there is a moment at BA at support B, then there will be a rotation at A, and that rotation needs to be prevented. So if B, so for example here we have a moment BA 67.5, so that 67.5 is counterclockwise, so clockwise because positive, so that clockwise tend to rotate this in this direction, so it tend to rotate like this, and then here it should keep it flat with 0 slope, so then there it should apply a moment as well, another clockwise moment to keep that 0. So that moment we have proved to be half of the moment on the other end. So here there is a carryover that we call a carryover. It is 33.75. okay, so that is because of the moment FBA. Now if you have a moment FBC, so FBC is 33.75 FBC, and that will not have a carryover on C because we assume C to be 0. okay, we assume C to be a pin joint, so there will not be a carryover from BC to the support C. But this 120, that is CB has 120, and that 120 will have a carryover at B, because if you have 120 that tend to rotate this one, and this B cannot freely rotate, so that free rotation is prevented by internal resistance, and that internal resistance is half of this 120. So from CB you have a carryover 60. okay, 60, that is half of 120. Now we have a situation where at AB 33.75. so at A, if you have a moment 33.75, 0 moment will be carried by the member AB, and entire moment will be carried by the support. So there will not be any need to balance this moment, because that support can absorb any amount of moment. But if you consider B, so here we balanced. okay, here when you sum these to 0, now there is a new additional 60, so that 60 is an unbalanced, because BA 0, here 60, so we need to distribute. So 2/3 So 2/3 is 40. So minus 40 here, minus 20 here. So now this is balanced. In this column it's minus 40, in this column it is plus 40. So it is balanced. Now here there is nothing, no other moment. So here it's everything balanced. So now what happens is this minus 40 BA will have a carryover of minus 20. And this BC will not have a carryover to the support C because support C is assumed to be pin. So now there are no other moments in any other support B or C. So now this iteration can stop. So in moment distribution method, what we do, we sum entire moment. So from here we sum everything. So we sum everything and put it here. So it's 33.75 minus 20, that is 13.75. Here it is 67.5 minus 40, that is 27.5 plus. So here is 100 minus 100.25, 33.75, so that is minus 67.5, and here plus 60, so that is 6 points minus 6.75 minus 20 minus 27.5. Here 0 plus 120 minus 120. So now you can see at all these points, here it can carry a net moment, here it can't carry and it is balancing, here it can't carry, it's balancing. So the net moment at B is 0, net moment at C is 0. So now if I write this down, if I draw this beam, so here I have a support A, so I have a vertical, here another vertical support. Okay, now there are no load acting on this, but there is a moment that is 13.75. So that is clockwise, right? Because positive 13.75 at, so there is A and B and C and D, and at B at B on BA segment, so at BA segment is 27.5 plus, so that is 27.5. Here it is negative minus 27.5, so that is in the other opposite direction. Here it is 120. Here you have a load that is 40. This distance is 6 meter, this distance is 9 meter, this is 4 meter. So now you have all the moments 13.75, 27.5, 27.5, 120, 120, 40, and then you have a load also 10 kilonewton meter. Now because of these n moments, I can even break this into AB and BC. So if I break into AB, so I don't know this reaction RA, RB1, but I know the n moments. So n moments is 13.75 and 27.5. So here also I know the n moments, but I don't know. So here reaction, so RB2, RC1, so this is 9 meters, this is 6 meters. So here 27.5, here 120, and there is a load acting on this one. So here if you consider this component RC2, then there's a moment 120, there's a load 40, and the distance is 4 meters. So now each of these individual segment has 2 reactions, and you can take individual segments and solve and find the two reactions. And here you can find the two reactions. The total RB is going to be RB1 plus RB2. Total RC is going to be RC1 plus RC2. Because if you can do individually and plot bending moment shear force diagram, you can merge them into one diagram. Okay, we'll see that in a different example how to, when you merge, or even we can do on this problem. So now these are the end moments. Now if we go back to the slope deflection equation problem, so I hope we did this same problem. So that is this one. Okay, so we should have got the same answer. Here you can see 13.75, 27.5, 27.5 minus 120. Actually the sign convention here, fixed end moment, we have a different sign here. So if you consider here, it is plus 13.75 plus 27.5 minus 27.5. so here it is minus. So we assume the fixed end moment in counterclockwise to be positive. Okay, so when you consider BC, we consider counterclockwise, fixed end moment is positive. Actually, as per the book, clockwise moment is positive, so you please correct on this as well. So when you assume a minus, then you will get the minus value. But whatever the sign convention, what is important is the what you understand. But because here you see, you get everything same. Here 13.75 clockwise, so whatever the final results is going to be same, but your assumption is that sign convention is consistent, but it is different from the one we are now using for moment distribution. But what we are using for moment distribution is the correct one. So like this, if you do this, if you take the segments, so we can do this one and we can plot the bending moment shear force diagram. Let me shift this second problem a bit down, so I will have more space to solve this problem. Okay, so this one we can do in a different video. So now if I take this so here if I consider this RA plus RB1 is 0, so and take a moment by A, if you consider RB1 into 6 minus, that is counterclockwise, this is 13.75 minus 27.5 is 0, so RB1 is 13.75 plus 13.75 plus 27.5, and that you divide by 6.875. Okay, so 6 point, I don't know why we got wrong. Here we made some mistake. It seems here it should be minus. Okay, so there's a mistake here, so this should be also, so in slope deflection also it is 6.875, so RB is 6.875, 6.875, so minus 6.875. Okay, so RA is minus 6.875 because RA plus RB is 0. Now if I consider that I have now the reaction, so that is RA is minus 6.87, so it's downward. Okay, so it's acting downward. So 6.875, and you have 13.75, and you have 27.5, and you have a vertical of 6.875. So if I plot the bending moment diagram, or shear force diagram, I have 6.875, so that is downward. Okay, so minus 6.875, and there is no, if you take an arbitrary section, so that arbitrary section, if you take an arbitrary section, you have 6.875, and then you have a moment that is 13.75, and your V and your M. So 6.875 plus V is 0, so V is minus 6.75, and this is applicable between A to B, so it's a constant shear. So 6.875, and it becomes 6.875 to 0. Okay, so your shear force diagram is this. So that's the negative constant shear. And if you consider the bending moment diagram, so this is shear force diagram. You consider the bending moment diagram, so you have a fixed end moment here, that is 13.75. so this is a positive because it's going to sag that element. So it is sagging, so it's positive, so that is, you have a 13.75, and then here you have a moment 27.5, that is hogging, because it's tend to hog the, so it's minus 27.5. And you know that the first derivative of bending moment diagram is shear force. So shear force is constant, means that bending moment diagram also constant. So even if you take this arbitrary section X, so M, so that is, if you take equilibrium, M minus 13.75 plus 6.875 into X is equal to 0. So it is linear. So it's going to be a negative curve because your shear force is a negative value. So this is the bending moment diagram between A and B. So bending moment diagram. So if I consider the segment, the next section, that is BC, so you have RB2, RC1, then you have the moment 27.5 counterclockwise, 120 clockwise. And then you have a load acting on this one, that is 10 kilonewton per meter. Now if you consider the equilibrium equations, so RB2 plus RC1 is equal to 0. You take horizontally, all the forces are 0, and then A is 0, so then you take moment by B, so it is RC1 into 9, the distance is 9, then you have plus 27.5 minus 120, then you have another moment minus 10 into 9, is the 90 kilonewton acting at the middle, 0. So let me check. So here it is RB plus to RB. Oh, I made a mistake here. So RB2 plus RC1, then you have to consider the load. Minus 90 is 0. So RB2 plus RC1 is 90. So like the slope depletion equation. Then you have the moment 27.5, 120. Okay, minus 120. Then you have the segment BC, but actually the segment CB should be taken separately. Actually this moment is wrong here, so let me correct that one as well. So RC1, RC2. Okay, so this is a correction on slope deflection equation. So here RC1, this is a correct equation. RC1 into 9, 27.5 minus 120, that is the moment here, minus 10 into 9 by 2. So here 9 RC1 is equal to, so if we take this here, 810 divided by 2, that is 405 plus 120 minus 27.5, and that divided by 9. So this is 497.5. so RC1 is equal to 55.3 kilonewton. Okay, so that is obtained by 9 into 9, 90 into 9 is 810 divided by 2, that is 405 plus 120 minus 27.5, that is 497.5 divided by 9, 55.27 or 28, but it's 55.3. Then RB2 is 90 minus 55.3. So that is 90 minus, that is 34.7. That is 34.7. This should be corrected in the slope deflection equation as well. Okay. So RC1 is 9, RC1 is RC1 is 55.3, and RB2 is 34.7. So now let me move this further. So I got the reactions for RB2 and RC1. Now I have those reactions. Here this is 34.7, this is 55.3, 120, 27.5, and you have a load acting on it as well. So now we can plot the, or we can take an arbitrary section. So that is 34.7. Yeah, some load, and yeah, moment 27.5. So here Vm. So if you take equilibrium equations and derive an equation for V and M, you will get the equation for shear force and bending moment. So you'll get a shear force, say 34.7 here, 34.7 shear force here, and here it is 55.3. So that is minus 55.3. And the shear force is changing because, for example, the first derivative of the shear force is a negative of the load. So now you have a positive downward load. Okay, so your shear force diagram should be a negative slope, so that you will get a positive load which is acting downward. So now if you get this V, 34.7 minus 10x minus V is equal to 0. So V is equal to 34.7 minus 10x. So that is the line. This is the shear force diagram for the segment BC. And if you SFD, if you consider the shear bending moment diagram for BC, so now here this is AB. Okay, AB. So the bending moment at B is 27.5, which is hogging, so it's negative minus 27.5. Then here it is again hogging, negative minus 120. So between these 2 points, your bending moment diagram is going to have a positive slope here, because the first derivative of bending moment is shear force. So this slope of the bending moment is positive, it gradually goes to 0, then it's increasing in negative direction. So now we can check whether this line, this bending moment diagram, is going to be a shape like that, or it's going to be a shape like that. Okay, there are two options. So the best way is to see whether this bending moment diagram will have a 0. Okay, so 0. So now, for example, if you consider in this case it's minus 27.5. okay, and if I derive the bending moment diagram equation, so at x, mx counterclockwise plus 27.5 minus 34.7 into x, so that is the x, so 34.7x, then plus 10x into x by 2 is 0. So now mx is equal to 34.7x minus 5x squared minus 27.5. So now if I put this into a quadratic equation into the calculator for mx is equal to 0, I can find the value for x. Okay, so if there is if this bending moment diagram is going to cut this horizontal line, then you will have a mx, when mx is equal to 0, you will have two values for x. Okay, so let's do that one. So if you substitute mx is equal to 0, 34.7 x squared 34.7x minus 5x squared minus 27.5. So x is measured from support B. So now in this case if I use a simple online tool, say here A is minus 5x squared and here the B is plus 34.7x, so plus 34.7x minus 27.5, so that is C, minus 27.5. so in this case say it's 0. So for this equation there are two values, one is 0.9, other one is 6.027. so it cuts the horizontal x-axis. So in that case you will have a curve, so that is something like this. Okay, so that is the bending moment diagram for BC. So similarly, if you take CD, so CD component has RC2, then you have a moment 40, the force 40, and you have a moment 120. So this is simple. If you balance vertically, you get RC2 is 0. RC2 is 40. Okay, let me further push this down. So if I plot the shear force diagram to this, okay, shear force diagram to this, so it is 40 here, so 40, and then it's constant because there is no load between, so that is the shear force diagram. And the bending moment diagram is, you have 120 which is Hawking negative, so minus 120. Then since shear force is horizontal, so it's the linear one, so that is how your bending moment diagram looks like, shear force diagram. So here BM, SF, B. Now if I want to plot the whole bending moment diagram to AB, the entire beam, I can simply merge. Say I can have this bending moment diagram plus this this shear force diagram, SFD1, then SFD2, and SFD3. So if I take the beam, so if this is the beam, so A, B, C. So between A, B, this is the bend shear force diagram, minus 6.875. So minus 6.875. Between B and C, it is 34.72 minus 55.3. 34.72 minus 55.3. So that is 34.72 minus 55.3. So that is drawing a straight line. Okay, I hope you. So that is the minus 55.3. So that is the between B and C. Okay, shear force diagram 2. 3 is constant 40. So that is 40. Okay, 40. So the reactions, so So for example, is 6.875. So 6.875 for RB2, and our RB2 is 34.7. So this is the shear force diagram for the beam. Similarly, I can plot the bending moment diagram by just merging A, B, C and D. So between A to B, it is the linear curve. So 13.75 to minus 27.5. So 13.5 to minus 27.5. So that's the linear. And then you have a so 27 minus 27.5 to minus 120. Then you have minus 120 to 0. So this is the bending moment diagram for the. So if you know this end moment, you can split them into 3 segments or whatever the segments depending on the problem and solve it. So this is how you approach a moment distribution method to solve a beam. So if this beam could be anything, it could be some real life problem. Anything you can solve using the moment distribution method as I have shown you. So I'll post another example on this moment distribution method, and I'll post further examples on conjugate beam, slope deflection and moment distribution as well. So this lecture, this discussion ends here.